There we go. Okay. This is, can you see the,
Yes.
awesome. Um, okay. Let me start out with thank yous. I'm delighted to have this opportunity to share this work in progress with you. There are so many people at Haifa that are doing important work, and I want to thank all of you at the center for hosting me. So Eldar, it's great to see you. Other people from the center have come and visited Berkeley, including Neva Elkin Koren. It's been really neat to see her. Amnon, you've been a lovely colleague, and I really mean that. Amnon has always been willing to interact, to press the bounds of this project, and he really helped me see some contours of it that I could not see. So I am in debt to you. Tal Zarsky, your dean, I believe Tal is your dean now, is that right? He's
Nice.
part of my academic community, and he's really a generous participant in it. And I'm grateful to Professors David and Guron for giving commentary, and apologies for all errors. I really want to learn from you too, so tell me what I've got wrong. Tell me what insights I can gain from your experience for this project. So to explain the project a little more deeply, I'm going to give you my roadmap. This is a book project with Simpson Garfinkel. Bizarrely, the way this started is that Simpson and I were flying back together from Tel Aviv. Well, we weren't flying back together. I was sitting in my chair, and Simpson came and sat next to me. We talked for about 11 hours on the flight back, and we agreed to write this book together. It's forthcoming from Cambridge University Press, and it's about quantum technologies broadly. And by that, we mean technologies that use quantum effects for some type of utility. So we've divided this into quantum sensing, computing, and communications. Our book then, after describing the technologies, discusses possible scenarios for these technologies' deployment. And then those scenarios make it possible to kind of noodle through policy issues. I want to warn you about one assumption in my work. I am very skeptical of claims that technologies are novel. And I think novelty often makes it harder to understand and see patterns in the history of technology. So one of the things we're trying to do is figure out what about quantum technologies truly is novel versus what are the things that we can use existing metaphors, existing regulatory approaches to kind of think through the problems presented and the opportunities presented. So why is quantum technologies exciting now? A whole bunch of reasons. Huge amount of state investment. A lot of the state investment out there from countries like China and blocs like the European Union are explicit in their desire to overcome American dominance in internet technology. So there's a kind of explicit, we're going to build the next generation of technology and we're going to make billions after we've created it. A couple other military related issues. There are interesting countermeasures that could be used. Quantum technologies could provide countermeasures for some forms of SIGINT that are interesting. There are interesting shifts. There are interesting developments in electronic warfare where quantum technologies might provide new countermeasures against electronic warfare that are valuable. There's the issue of measurement and signals intelligence, MASINT, that I think is going to be important and be more greatly enabled by quantum technologies. And then it's just easier to do. It's easier to develop some of this technology because some of the technology has become commercialized. For instance, the image above is from Thor Labs, and this is a quantum eraser demonstration kit. This is literally an experiment that was invented in a laboratory just a decade ago, and now you can buy a working model of it for about $4,000, and that's fantastic. I mean, that was state of the science research just a decade ago, and you can buy it. And similarly, this other image, I think it's right above my head, the IDQ quantum random number generator. This is a commercial product that you can buy on the internet with your credit card and deploy a quantum key distribution network in your company if you wanted to with off-the-shelf hardware. That's pretty cool. So that's making it easier to develop in this space. A couple other things are going on. Corporations are interested in quantum technologies for a whole lot of different reasons. In my research in PitchBook, and the other service, I can't remember what it's called right now, I find that there's about 200 companies that are public and private that have some type of significant quantum technology focus. Some of those public companies are old tech giants, companies like Fujitsu and Hitachi. So the quantum portfolio is a very small part of their overall work. And then there's some private startups that all they do is quantum technology, and many of them don't even have a product out, but they're out there. Why are companies interested? Well, among other things, they want to get their employees ready for the technology. So there's a value in practice and becoming familiar with the technology, even if it doesn't have immediate utility. There's a fear that quantum technologies could be winner take all or winner take most. And I'll give some examples of why that could be the case in a moment. And of course, companies have big challenges in this space. The President Trump administration has really levied a kind of export control battle to try to control some of the precursors for quantum technology. So for instance, we are trying to export control dilution refrigerators, which are necessary for many forms of quantum computers. And there's other challenges, understanding what is real, what will really work versus what is fluff, and also figuring out what your path to profit is. There are companies out there, it's not clear to me at all how they're going to actually make money doing what they're doing, but they're trying. And of course, the US government has got a strong industrial policy approach. We're pouring billions of dollars into basic and applied research in quantum technologies through the labs. So very quickly, and this is just, I pulled this right out of our book, who is publishing in quantum technologies? Well, you can see that there's a lot of interest in China, and there are many labs and a lot of money flowing into research in China, such that perhaps they've done more publication than the US and European authors. However, when you flip this analysis around and you look at impact, US and European authors have more impactful papers. What's happening in ramp up of workforce? Well, we're seeing a steady and a strong increase in master's and doctoral candidates studying quantum information science generally. So almost 5,000 theses a year coming out of institutions. What are those institutions? Well, they're the bedrock technology giants in the United States: MIT, Caltech, the UC California system. But there are also significant concentrations in the UK and in Canada. Canada's got a lot of development. And of course, a lot of the training is coming out of institutions in China. So Tsinghua is up there with over 100 theses already published on quantum information science. So on to the technologies. I'm just going to be very brief because I wanted to throw out lots of threads so that Tal and Shai could pick up the threads they wanted to go with. What Simpson and I think is that the killer app in quantum technologies is sensing. And there's a couple different reasons for this. We think for the next 10 years, sensing is going to be the most exciting field. Well, why? Sensing is already mature technology in a sense. The MRI is a quantum sensor, for instance. Sensing is becoming easier. The components in some cases can be purchased, and we're finding more and more interesting applications for quantum sensing. So the medical ones are obvious, and they've been with us for decades, but there are other interesting ones. So the US military, well, militaries generally are very interested in PNT technologies, so position, navigation, and timing technologies like GPS that are resistant to electronic warfare. So our GPS constellation was the first to make it into space, but it is extraordinarily vulnerable to jamming. It's very easy to jam GPS. In fact, in the United States, you can buy a GPS jammer that plugs into your cigarette lighter in your car for like $12. And truckers buy these jammers so that they can't be tracked as they're driving their routes. So there's an interest in creating quantum positioning devices that could go in jets, that could go in submarines and the like. Interesting thing about them is they work underwater. they're thought to work underwater, they're thought to work underground. So this is a way of replacing or supplementing inertial guidance. There's been a lot of talk about quantum radar, although it looks a little bit overhyped. But the idea here is that you could spot low observable aircraft using a photonic sensor by retaining an entangled photon and then sending another photon out through your radar array that possibly hits a stealth jet or not, and your retained photon would reflect that. This appears to be a little overheated, but there's a similar application for sonar that doesn't look so overheated, and it looks like it has a lot of strategic consequence. So with a quantum sonar sensor, one could imagine building an array, let's say in the South China Sea, to detect the entrance and exit of submarines based on the heavy metals that are in those submarines. Let me just last mention that mining and extractive industries are very excited about quantum sensing. And in fact, when you look at the companies that are pouring money into the field, you see companies like Schlumberger and De Beers, because they have a suspicion that they can use quantum sensors like the one hung from this helicopter here to find extractive material. And so that's really interesting. And we could noodle on whether that means there will be more or less mining in the future, or whether it will be more precise or not. Quantum computing is what everyone's excited about. And let me just say a couple things about it. These devices are still mostly research curiosities. The one I have displayed here is actually extraordinarily neat and tidy compared to the ones we have at Berkeley that look like they've been attacked by rats and, and are in a pretty a state that clearly is not ready for production. Another thing to know about quantum computers is that they do not consider all possible solutions to some given problem and spit out the answer. Instead, certain algorithms have been discovered for quantum computers that solve certain problems faster. And of course, we know about the idea that some of these algorithms will do things that will undo encryption more quickly than a classical computer. But the key and the point that Simpson and I really are making strongly in our book is that chemistry, the simulation of chemistry, is far more important economically than the crypto attacks that occupy the attention of the media. So if you can simulate chemical interactions, we could have fantastic discoveries that could make the world better in all sorts of different ways. But it's also the edge of the winner take all issue here. So if you look at Google, IBM, all the serious competitors in this field, you ask them, well, what are you doing with these devices? Well, the first steps they're taking are in material science and in chemistry. The reason why is that you could use a quantum computer to make fundamental insights into material science that help you build a larger quantum computer. And that's how this could be winner take all. Let's say IBM makes that fundamental step that allows them to grow their quantum computer from 60 qubits or whatever it is today to 600. If they can keep that insight secret, they're going to run away with the prize. And so that's the sense in which we think that quantum computing could be winner take all. Quantum communications we deal with last in the book. What's important to know about this field? There are two high-level categories, or at least that's how we think of it. In one, quantum effects is used to make classical encryption more secure. So this is quantum random number generation and quantum key distribution. The goals here are to exchange keys that are then used with classical technologies, the telephone, the internet, to be secure in a manner that they will retain their resilience even against a quantum computer. And then the second category you might call quantum networking or quantum internet. And this is the idea that you would use quantum states themselves to communicate. So just imagine if instead of communicating with the light, the chroma of the light in the fiber optic cable, you communicate with the spins of photons. The advantage of that would be that if an eavesdropper were present, the photonic spins would be measured by that eavesdropper and corrupted by it. And then you would know that someone was spying on you. And that is new. That is not, an improvement on existing capacities. There is no way to know today that you're being spied on. This technology gives you a way to know something. That's very exciting. So after introducing the three technologies, we discuss a series of potential policy scenarios, and these go on and on and on. So I'll just mention them briefly. We model a world where governments take off with quantum technologies. They get the best quantum sensing, the best quantum computing, and then use their superiority to deny access to those technologies to others. So that's one scenario. The scenarios we think are more likely are in the middle here, and this is the idea that there's a public-private collaboration that results in huge discoveries and sensing and computing. And you could imagine one that looks like the internet, where it's an international collaboration and so on, but you could also imagine one that looks a little bit more like the Cold War, in which China decouples from the West, and they go in their own direction with quantum technologies, and the US and Europe take a different path, and there's secrecy and a lack of collaboration between the different blocks. And then finally, we model a quantum winter, and that's the idea that, we're just not ready yet. These technologies are promising, but we cannot realize them in the next 10 or 15 years. So that's the final scenario. And what I'll do is I'll just go through and list some of the policy issues, and I hope what I could do after introducing them is see what threads we'd like to pick up on and discuss. So one major point of our book is to explain the limits of what we think quantum computers will be able to do. So we spend a lot of time trying to solve the notion that quantum computers can't solve all problems instantly. Instead, there will be a series of discrete problems that these devices are trained upon in many different fields. The biggest threat of quantum computing is not actually cryptanalysis, but rather whether quantum computing begins to unravel computationally complex problems, thereby leaving the human fewer and fewer job opportunities, right? Like the things we do today as workers that computers can't do, maybe quantum computing begins to unravel those. And I think that's the biggest strategic implication of quantum computing. We also talk a great deal about virtuous cycles and how to create virtuous cycles in quantum computing, just as we've seen them in classical computing. In classical computing, the introduction of computers to the consumer through the personal computer created an unparalleled virtuous cycle, where computers got faster and faster and faster and cheaper and cheaper and cheaper, and we've woken up today and now there are little computers in our socks. How do we create such a cycle in quantum computing? That's highly related to the next topic, and that's the network effects issue, and whether quantum technologies are a winner-take-all environment. One of the things you see companies doing in this field is offering access to their early quantum devices via the cloud. And I think there's a lot of strategic advantage to that. One is that you get to keep your engineering secret, right? You get your quantum computer is inside your warehouse, and only your engineers get to actually see the engineering, yet you still get to sell the advantages of the device. I think there's going to be, that's a deliberate strategy to win the engineering part of these issues. We talk a great deal about freedom to experiment. What it would mean if what it would mean if there's too much secrecy around this. What it would mean if companies like Google closed their labs. So many quantum ideas in quantum computing actually came out of academic and industry collaborations where there was fat in the system, right? There was some ability to explore ideas that might have been even considered fringe. Immigration and diversity is really important. Everyone we've interviewed has said that having an international team is key. There's one consulting group put out a study a few years ago saying that there's only 7,000 people in the world who are trained to do quantum technology. And so you can't build a company without having liberal immigration. And even when we spoke with John Wei Pan, who's the father of quantum in China, the inventor of that amazing device on the earlier side, and the person who developed China's satellite-based quantum communication system, he told us that his lab has lots of international visitors, and that he thinks that it's not possible to be competitive in this area without having these types of collaborations. So openness is a related issue. If you think back to the Cold War and the development of computing, there were a number of technologies that arguably had very important national security implications. The transistor is one. So the transistor gave the United States advantages in its ICBM development over the Soviet Union. There could have been a case made to keep transistors secret. And what would that have meant for computing, for what we're doing right now, if the transistor didn't have parallel development in the private sector? You could say the same thing for lasers. Lasers arguably should have been a secret technology, but the fact that so many of these technologies have parallel invention in the private sector has meant that we've had a consumer revolution with these technologies. I think that's important for quantum too. Industrial policy is at the heart of our book. It's hard to tell how much China has put into quantum technologies. I think it's at least $3 or $4 billion, but it might be as high as 20, depending on what you count as a project. In the United States, we're now spending in the billions, and the interesting problem now faced is that there's more money than talent. And the program officers I've spoken to have told me that investigators are writing quantum into their existing research protocols in order to capture these new monies that the Trump administration is distributing. We talk a great deal about strategic competition, really interesting developments that can take place. We think that we think quantum sensing is going to be really important for intelligence, surveillance, and reconnaissance, and the advantages will rebound mostly to nations that have space programs. You already see all sorts of experiments surrounding putting different quantum sensors into space, and this is going to be really important for discovering enemy or adversary material and so on. We think there's going to be much more attention. Quantum sensing is going to bring more attention to measurement and signals intelligence and geo intelligence from signals intelligence, which we've seen has been the real dominant focus in the last 10 years. I explained the stealth issues, but I think where this comes to is that the militarization of space is partly related to this revolution of space-based sensing and space-based communication. So the fact that we see the development and the elevation of the United States Space Force and all the anxiety surrounding anti-satellite is in part related to satellites as platforms for communication and sensing. And so let me wrap up with this, say that we also discussed the idea that quantum technologies could be inherently political, in the sense that Langdon Winner used that term in his fabulous book, The Whale and the Reactor. The quantum technologies have some of the characteristics of earlier technologies that were political in Winner's sense. Essentially, only elites understand and have access to these technologies. There is a very strong military forward focus on investment. And in fact, if you see what's happening in the United States, the research money is coming in through the national laboratories. And that is an attempt. I mean, one advantage of that for the United States is that if you take that money, it's much easier for the government to declare your research secret. And this is why you see Google tacking the other way and kind of refusing government money in their quantum technology space. And so one of the questions to consider is, does quantum suffer what early computing did? So if you think about computers up until the 1970s were largely associated with the military and with large companies, and there was like almost a taboo in computing that it was a technology that really served the powerful. And so are we setting up quantum technologies to have the same type of taboo by how we're investing in them and the secrecy that is surrounding them? So with that, I hope I've provided plenty of room for conversation, and I am going to be quiet and listen to your reflections. Thank you. Oh, you're muted.
Wonderful, Chris. That was certainly fascinating as anticipated. Without further ado, Dr. Tal David, your take on it.
Okay, thank you, Amnon, and thank you, Chris, for a very interesting presentation. That was excellent, and I apologize to everyone if I repeat a few of the things that Chris was talking about, but I'll try to give a different point of view. So first correction for you, Chris, I'm not a professor of any kind. And certainly I can say that I'm the least knowledgeable person here today in terms of law and policy, but I do know a little bit about the technology and the science. So I'll focus about that. As I share my screen, I'll tell you a little bit about myself. Do you see my screen? Good. So I did my PhD in quantum physics, studying cold atoms, mostly for quantum sensing applications. And then I went to the industry. I worked both in the laser field and then in quantum magnetic sensing in one of the defense companies in Israel. And for the last about 7 or 8 years, I'm managing research and development for the Israeli government. And since exactly a year ago, in December 2019, we have launched the Israel National Quantum Initiative, and I was appointed to run that for all of the government R&D agencies that you see down below on the slide, the Innovation Authority in the Ministry of Economics, which pushes the industry forward, the Council of Higher Education, which funds all of the academics here, probably people know them, the Directorate for Defense Research and Development in the Ministry of Defense, the Ministry of Science, which for people coming from abroad, I must say, it's a pretty small endeavor, although they have the largest logo, and of course, the Ministry of Finance. So in this presentation, I'll try to give a little bit of a background of what quantum is and where do we find it and why is it so interesting. And also I'll say a few words about what's happening in the world and what's happening in Israel. So let's begin. Okay, so when we say quantum science and technology, what do we mean? We mean take all these unfamiliar or complicated concepts in the middle, like quantization or wave-particle duality or the uncertainty principle or quantum entanglement that was already mentioned before, and directly from that, realize components, systems, capabilities, and services that have typically either a very good performance, sometimes orders of magnitude better than any other alternative, or in some cases, like was mentioned about quantum cryptography or quantum communication, realize capabilities that you cannot do without quantum principles. And if we put quantum science and technology on a timeline of the last century or so, then we can roughly put 3 milestones on that. The first one about 100 years ago was the discovery of quantum physics and the definition of all the laws and governing phenomena. Then the first technological revolution was in the 1950s, 1960s with the invention of the transistor and the laser and the maser, and a little bit later on the GPS constellations. And there you could say that the quantum nature of these technologies was microscopic or an ensemble use of quantum properties. And now in recent years, there's what we call the second quantum revolution or the second technological revolution. And in this era, we're accessing much more intimately on the single quanta level, single photon level, single atom level, advanced phenomena, and can push the technology much farther away. And the impact of this field is really, really wide. You see that, you see time tagging in finance, and you see satellite technology that was also mentioned. You could see material optimization and drug development. Everybody in the last year has been looking at COVID-19 with a huge effort of mapping the genome within, I don't know, a few days since the virus was publicly published in China, and the huge effort of all the pharmaceutical companies to develop these drugs. So usually when a drug is being developed, it's like a decade and $1 billion process. And now we've seen that if you focus all of the computing power, you can do it much faster. And quantum computers will be able to do that much, much faster than that. And I'll say a few words about that in the coming slides. So the impact is huge, both in the civilian area and also in the defense or military area that I'll say a little bit less about here. Looking at global money, so this slide is a slide that we need to keep updating all of the time. It's already obsolete all of the time. And the numbers here are in millions of dollars, usually over a 5-year period, although in some cases it's a little bit more or less than that. The last, I think, 3 big ones are Germany, that added 2 billion euros for the next 4 years for quantum information as part of their exit strategy out of the COVID-19 crisis. They said we have to invest in boosting the economy in specialized capabilities, and they chose that. And this is on top of everything that they have poured in the last few years, and the European Union flagship program, which is in itself is a €1 billion program. Still, they have some arguments there. On the US, this number represents the US national program, which is a joint venture of the National Science Foundation and the Department of Commerce and Department of Energy through NIST and through the national labs, as Chris outlined before. But this number does not show what happens in the Pentagon. This is not a publicly released number, but it's safe to say it's not a very much different number. So you can probably double that number for the US investment. And also India joined more than $1 billion program just a few months ago. And of course, before that, we have the Chinese. The numbers are huge, and they keep going up and up and up. And apart from all of these governmental programs, you have a lot of companies or corporations going into that. Chris said 200. I think we're way past that now. As I'll show in a few slides, only in Israel we have about 25. So this is going very rapidly. So probably most of you have heard about the quantum computing activities by Google or IBM or Microsoft or Intel, but it's much, much more than that. We have Toshiba going into quantum communication. We have Volkswagen doing quantum simulation and computing. We have Citibank and JP Morgan Chase doing optimization of finance portfolios. We have Alibaba, that everybody here probably bought something from AliExpress at one point or another. They're pouring $15 billion in AI and quantum computing in the next decade. This is huge. And of course, we have other representatives like Honeywell and also Grumman, Airbus, Thales, and so on and so forth. So this is really buzzing about. If we look at the applications, what we can do with quantum science and technology, so we'll separate that into 3 main ones, like Chris said. The first one is quantum measurement or sensing or metrology. The idea there is that because atoms of a certain species are all alike and their internal structure comes from fundamental constants of nature, we know how to describe the internal structure of quantum systems very, very accurately. And this leads the way to using that understanding of the internal structure of quantum systems in order to make very precise measurements. So we're talking about measurements of time or frequency using atomic clocks. The most accurate atomic clock, if it had started ticking in the Big Bang, until today, it has not lost even a tenth of a second. Okay, this is what we're talking about here. We can measure fields or interactions like magnetic fields or gravitational fields. So for example, companies like Noble Energy that are searching for deposits of oil or gas, they need to find this anomaly. And they're doing seismic and magnetometry and gravitational surveys. And one of the things that will interest them more is to be able to measure these things continuously and to understand how much is there left in that reservoir, something that is not really easy to measure today. We can also measure forces. So gravitation is a type of acceleration. We can measure linear acceleration and rotations and doing inertial navigation, really in the utmost and most strategic performance levels that you can think about. So for the Israelis here, everybody know that we buy our submarines from Germany, and the submarine is a platform that is strategic and likes to be covert. Doesn't want people to know where they are, so we can understand that if a submarine leaves the shipyard in Germany and bypasses all of the Mediterranean Sea to arrive to Israel, it would like to be as much as possible not on the surface looking for the GPS signal to understand where they are, because inertial measurement systems always drift, so they need to get a fix. So if they have a very good inertial system like quantum inertial systems, they could do the whole trip about a month without surfacing at all. The second application field is quantum communication or quantum cryptography, and I separated that into two. I think it's more or less aligned what Chris was saying before. The first one is secure information, mostly how to distribute the key, the secret key between two parties that want to share information between them. And looking a little bit ahead into the future, it is the quantum network or the quantum internet that will actually use the quantum states for the communication itself. But this is a little bit farther in the future. And the third area of application is quantum information processing, which you can separate into quantum computing and quantum simulators. And the distinction there is like a simulator will be able to solve a particular kind of problem, like the analog computers that were around once before. And a quantum computer is like a universal machine that you can plug any algorithm, it will be able to run it. Not necessarily it will have an advantage about that, but they will be able to run it. And I always like to show this cartoon of what the Windows quantum computer will look like being simultaneously crashed or not crashed. Because the basic idea about quantum computers is that we take the principles of superposition, we're using that to put our bits, the very basic logical unit in a computer, not just in a 0 or 1 logical state, but in a superposition of both of them at the same time. And this gives us a possibility, together with other principles like quantum interference and entanglement, to be able to do some types of algorithms in a very efficient way and very fast way. And I'll say a few words about that as we go along. If we take these three application fields and put them on a sort of a qualitative graph, it's not quantitative in any way, of the level of maturity versus time. So we see that quantum sensing is the most mature vector, as Chris was mentioning. We also already have many quantum devices, mainly clocks, but also other devices already being used commercially in the field. And this is going to become more precise, more multi-sensor systems, and more low-cost, high distribution, massive distribution of sensors, and not just special purpose, room-sized machines. Interestingly, this is the vector that today receives the least amount of attention. Okay. Perhaps maybe because it's being blacked out in some places around the globe. I'll say, and I'll give an example, I think, in a couple of slides about that. Quantum communication or quantum cryptography lags behind in terms of maturity, but it's ramping up really, really fast. We see already today the quantum random bit generators as commercial products. We see quantum key distribution networks already being employed and providing commercial solutions. And we're seeing this becoming more and more complicated with the satellite quantum key distribution that the Chinese have launched into space. I'll also say a few words about that in a second, and so on. Then you have the least mature vector of quantum computing that receives the highest amount of hype and the highest amount of money invested in it. A very difficult one, very far away from us. But what's very far, this is something that it's a matter of how optimistic you are. So if you're looking at the end of it, of quantum computing for breaking codes and destroying all the cryptography that people are using today, this is perhaps the most farthest away application for quantum computers. I'll say a few words about that, but it's not that far away. What we will see much before that, and we're already starting to see that today, is optimization problems, therefore materials and drug development that I mentioned before, and then quantum AI or quantum computing intelligence and so on. Just today, there was 2 papers that were published saying that quantum computers will not only be able to solve linear equations exponentially more efficiently than regular computers. So in the area of COVID, everybody knows what an exponential graph is and how it's important, right? But now there was a discovery that also nonlinear differential equations could be solved, and this opens a whole new world of problems that quantum computers will be able to tackle. So these last 2 slides talked about what are the application fields. This slide shows how do we build these things, okay? So in order to get access to the properties and phenomena in quantum technology, we have to go to small length scales, okay? So we're talking about atoms that could be at room temperature or a little above it. We can talk about atoms that are cooled to millionths of a degree above absolute zero, even a billionth of a degree above absolute zero. This was my PhD. Not this specific graph. This is the graph that won the Nobel Prize in 2001 for the bosons and condensates, but I did something like that. Atoms could be also charged atoms or ions. One of the most advanced ones in quantum computing today. We can also talk about photons. So we said that the laser is a quantum technology device, but it's been around for like 70 years. Today, when we're talking about quantum technology with photons, we usually mean few photons or single photon physics, okay? And also there's a bunch of other systems like solid state systems. This could be circuits and superconductors and quantum dots and color centers in materials like diamond or silicon carbide and so on. These are materials that are solid state, but they are engineered to behave like atoms. Okay, so I do them injustice and I call them artificial atoms and hope that they don't get too mad at me. So in the next 3 slides, I'll give a few examples of what people are doing with that technology today in the world. This slide shows a few examples in sensing. So on the top left, you see the American chip scale atomic clock. This is a DARPA project funded over $150 million, already privatized to a company that was called Symmetricon, then called Microsemi, then was consolidated by a company called Microchip. So big companies are buying small companies. And the idea of just, this is a small atomic clock. It is about 10,000 times more precise than the clock that you have in your phones or wristwatches. And this opened, and it's very low cost and small and low power. And this opened a lot of uses. For example, here we see a geophysical survey. There is a transmitter on this boat transmitting a sound pulse into the earth. And there's an array of microphones or geophones that each of them has a clock on it. And they're analyzing the time of return of the signals coming back from underground and understanding the structure of the ground beneath them. So this is used, for example, to search for oil, gas, or minerals like that. Okay, and this application alone sells thousands of clocks per quarter today. So this is a huge market that was not available before. In the bottom right, you see a similar technology of magnetic sensing, also used for geophysical exploration and also for other types of magnetic field anomalies. So for example, you could imagine the magnetic field of the Earth around us all the time. And if I put a sensor at some point and I have a car that has some iron or ferromagnetic material content moving around the vicinity of this sensor, it will deform the magnetic field lines of the Earth, and it will affect the measurement of this sensor. And this is how we can detect that something that has passed there. Okay. On the top right, you see a very small, you can see the scale with the quarter coin here from Northrop Grumman. This is a quantum gyroscope. This picture is from about 2014 or 2016. Since then, this has become a black project. You don't have any publication about that, but it still exists. And it shows that people understand that this is something that is strategic. All of these three examples are from atoms that are at room temperature or above. The last example on the bottom left is using ultra cold atoms at about 1 billionth of a degree or 10 billionths of a degree above absolute zero. And this is used to measure gravity. Okay, so the Earth is not exactly spherical. It has a topography and it has different layers and densities. And this means that gravity changes. So for example, if I go outside here in the street and I measure gravity, Newton told us it will be about 9.81 meters per second square. But if now someone will, build a huge underground parking lot under me, then you could say that there is a little bit less of Earth pulling me towards it, so the level of gravity changes. So just as a thought experiment, you could think about a hollow area underground, let's say something cylindrical, a diameter of 1 meter, very long, about 10 meters underground. I don't know why I'm thinking about that specifically, but you can think about it. The variation it will do to gravity on the surface of the ground is about 1 nanoG, so 1 billionth of the value of the gravity that we measure. So you need to have extremely good sensors and also smart algorithms in order to detect very small signals like that. Okay. Looking ahead at one of the dilemmas that we talked about, these sensors, a lot of them are already today export controlled by the US and other Western countries. Okay, we're already there. It's not something like in the future, and I'll get back to this issue later on. The next slide shows not sensing, but quantum cryptography or quantum key distributions. So Jianwei Pan, that was mentioned before, he's like the I would not call him the father of quantum technology in China. I would call him the general of quantum technology in China. Okay, and it's not that only he's attracting people from the whole world to come to his lab. He grew up in Europe. He did his PhD and postdoc in Austria, and then went home and became the leader of all quantum activities there. They have done two things in the last few years. On the right-hand side, you could see about a 2,000-kilometer line from Beijing to Shanghai through Hefei. This is their quantum center there, with local area networks for quantum cryptography or quantum communication. And this is not a scientific experiment. This is now being used by the banks and financial establishment in China for secure communication. Okay, so it's not a game, it's actually being used. On the left-hand side, you can see the cartoon of the quantum key distribution satellite that was launched to space already 4 years ago in 2016. This is a scientific experiment. It's a very, very low rate of transmission, but it's still something that is useful. The rumor says, or a very based rumor, I would say, is that when the Americans saw that, they called this the quantum Sputnik, because they understood that they've been caught a bit off guard. And this was one of the big drivers for the US national program in the last few years. So I talked about the export control issues in the last slide about sensing. So about quantum computing and also quantum cryptography, the US has declared that it is about to impose export control. They are about to put it into the ITAR list, have not done so just yet. But the very interesting thing about this is just a couple of months ago, the Chinese government, from the Chinese president himself, have also declared that they will export control quantum information. And this is something that you usually don't see from China, that they are limiting exports from their own. Another thing that is interesting to say about this is that if you look at, for example, patents, Chris has shown some data about academic papers, but if you look at patents, China are leading the US now in number of patents. You could say that they are junk patents. There are some claims about that, but still they are moving ahead very rapidly. And one of the biggest Chinese organizations that are writing patents in quantum technology, mostly in quantum cryptography and in atomic clocks, is the Chinese electric company, okay? Not a technology, provider. And they're investing very heavily about that. This slide shows a few things about quantum computing. I can go on and on about that, but I'll just say a few things about this. So we are now on the verge of seeing the first really useful applications for quantum computing. If you are on the optimistic side, you could say that in the next 2 years, we'll already be there. If you are less optimistic, you will say that it will take 5 to 10 years. And if you are very pessimistic, you'll say more. A few interesting things that have happened in the last few years about that. First of all, IBM, you can see their device here, have initiated a cloud service for their machines. The machines are in Yorktown, in New York, but you can access them right now from your house. Well, not right now, after the session will be ended, and play with the IBM quantum computers for free to some extent. And the more advanced ones, you have to start paying. But you could actually do that. And this formed an ecosystem of about 2 million users already today playing around, getting to feel how this computer is actually working, and developing new algorithms and new capabilities that were not here before. And this is a huge, huge thing. Another thing that happened also in the cloud business is that IBM is selling only their own service, but Microsoft and Amazon have already started partnering up with smaller companies and selling their services over the Microsoft or Amazon clouds. So I don't think it's necessarily a winner takes all. I think that this cloud infrastructure is actually a door that opens up to a sort of a supermarket of quantum services that will be using the cloud infrastructure of the big players, but it enables a lot of small players to go into that. I think this also has a lot of implications to policy and regulation and so on in it. Another thing that I can say here is, of course, Google has claimed about a year ago of reaching quantum supremacy. They have taken not a practical problem, some sort of mathematical problem, and they have shown that on their quantum computer in Google, they've managed to solve this problem in about 3 minutes, 200 seconds. And they have shown that even if they use the most high-performance computer cluster in Google, it will take them 10,000 years to do the same calculation. This started a little bit of controversy between IBM and Google about that. IBM said, well, not 10,000 years, only a few months, but still hugely impressive. And a very similar problem was shown by Chris from China only a few weeks ago with this million of mirrors and crystals on the optical table. That also started a little bit of controversy, as you always find with the Chinese, that people have some problems believing what they say, but it's very impressive. And I might say that all of the crystals, about 200 nonlinear crystals on that optical table that Chris has shown, are Israeli crystals made in Israel and being used in their experiments. A little company called Raycom. Another 2-3 things that I'll say about the slides. D-Wave is a Canadian company that has received a lot of, let's say, friendly fire in the last few years of how quantum they really are. Actually, what they are building is a quantum simulator and using that to solve optimization problems. So about a year and a half ago, they partnered up with Volkswagen, and they have demonstrated about 7 or 8 orders of magnitude improvement in the time of a certain algorithm that determines the optimal way to manage transportation in a city, to have the least amount of traffic and so on. This is a huge impact economically. So everybody that uses Google Maps or Waze always says it takes a lot of time to calculate the optimal route. So that's not a big problem. But if you talk about optimizing the whole transportation in a city, this is something that's very interesting. IBM a few weeks ago has published their roadmap on how their quantum computers will evolve. You can already start to define a quantum Moore's law in terms of not necessarily only the number of qubits, but also the quality of the qubits. So people are looking ahead, and they can already, after about a decade working in that, they can say where this field will go on. Of course, no one promises us that there will be no technological hurdles. Of course, there will be. And finally, the last graph that I added as Chris was talking about, so apologies if it's a little bit small, is a prediction that I heard from one of the top guys that are building quantum key distribution systems around the world, both in the US, in Switzerland, in Germany. And this graph shows the key size of cryptographic keys today being used, number of bits, roughly 512 bits or 1024 bits today. And this is the year. And the graph shows with the regular decrypting or factoring algorithms, what will be the trend of managing to crack these codes. So not much happening in classical computers, but already today in quantum computers, depending on your level of optimism, the expectation is that in about 2027 to 2030, the factorization capabilities will be here to crack codes. And this is much sooner than people have anticipated. And this is because people are improving the quantum algorithms all the time. And this is right around the corner. And if you have sensitive information, you better secure it already today, because 5 years from now, it might be cracked. This is a very important thing. It's not only a far future thing. People with sensitive information need to protect them already today. So yeah. Zooming into what happens in Israel. So in quantum science and technology in Israel, in academia is flourishing. We have an excellent community in academic quantitative measures like H-index and European Research Council grants and so on. We have a young community, but it's very, very small. It's about 140 research groups active today in the core of quantum science and technology. All of the universities, except for one, which you might guess which one it is, have established quantum science and technology centers today, bringing people together from physics and computer science, but more and more from engineering, from chemistry, from math, from philosophy. And some of them are only oriented in the law and policy aspects of that. I'll talk about industries on this slide. So when we established the national initiative just a couple of years ago, we counted about 4 or 5 companies active in this field in Israel. Not much there. Sorry. But in the last 2 years, we're now counting over 25 companies. Some of them are dealing with hardware, some with software, some with components, like the Crystal company that I mentioned before. Some of them are big companies, like Mellanox, that was acquired by NVIDIA this year, that are interested in clocks and in quantum key distribution, and further on in quantum computing, like the big defense companies that have been active in this field for quite a long time. Also, medium companies like Accubit making atomic clocks, and startups like Quantum Machines or LightSolve or Quantilar. And if we want to go into examples about that, we can go. I don't want to take up too much of the time here. When we formed the national initiative, we drew a few conclusions and identified a few challenges. One of them is that quantum science and technology is a strategic field, and it's here to stay. It's not something that will go over like a wave. And Israel needs to build on its heritage in information communication technology and in cyber and in AI, and position itself as a leader also in this field. We have to understand that quantum science and technology is not an evolution. It's not an incremental step. It's a change of paradigm. to build a quantum computer is not like, taking a few GPUs and a few FPGA chips and putting them back together. This implies that you have to develop an ecosystem for that. You have to think about how to do that, how to build the community, and what are the implications, for example, of what we'll talk about here in this sessions today. We also understand that in Israel, quantum science and technology is still in infancy. It's a small community. We have to look at it not only as a 5-year program, but in a longer vision that we hope that we can sustain. The main challenge is that we have a small community, human capital. Second challenge that is related to that is the fact that we need to have interdisciplinary and multidisciplinary approach. It's not like just physicists among themselves and computer scientists among themselves. We have to put people together in order to push this forward. Also, there's a matter of focus, what to focus about. We cannot focus on everything. Very interesting, I think, for the discussion today is the issue of international collaboration. For now, we would like to collaborate with everyone. We are not the only smart people on the planet, and we want to attract knowledge for us, but we also understand that the window of opportunity for collaboration in quantum is getting narrower all the time. Certainly in looking at China, but also some of our friends do not share all of the knowledge with us. I can tell you that one example that after one of the last conflicts in Gaza in 2014, we tried to contact some American company and ask them if they can help us, and they were not allowed to answer us that they're not allowed to talk to us. Okay, and this was a very high-level Pentagon policy issue. Yeah. Okay. So this is an overview of the components. In order to meet all of these challenges, we took a very holistic approach. We're not only building academic infrastructure, we're also investing in academic research. Only yesterday, we've closed the second round of a big fund, 150 million shekel fund for direct academic research through partly through the Ministry of Defense, but mostly through the Israel Science Foundation. So that just yesterday we received the second round of proposals for that. We're investing a lot in human capital, opening tens of positions in academia, scholarships for PhD students and postdocs, training programs for industry, and so on. We're investing in international collaboration, and we have 3 focus areas, one in quantum sensing, where we have a well-established industry for at least a decade. So we just need to push these projects forward. Quantum key distribution here seems a little bit small, but it actually grows very rapidly. Actually, the size of this thing today is about the size of this thing. So the program is getting larger than the numbers that you see here. And finally, there's the issue of quantum computing, where we have, less than 10 people in Israeli academia that actually know their way in quantum computing. We have almost 0 industries, although we have a few startups already in the last 2 years. And we asked ourselves, should we focus on that or no? And we understood that on the one hand, we have to grow the community, we have to enhance it. On the other hand, we understand the impact of this field. And so we took the approach of building a capability in Israel, both through using the cloud infrastructure state-of-the-art from IBM or Microsoft, but also building the capability in Israel. We're not going to beat Google or IBM tomorrow morning, but we have to be relevant enough so that the gap will not be too large, and we'll be able to take a decision once the community is enhanced if we want to take the next step and still be relevant for that. So this is a huge effort for us in the next few years. So my last slide is a few dilemmas. It's not well evolved like what Chris has shown over 5 slides, so sorry about that. First question is regulating research and technology. Should we take a top-down approach or a bottom-up approach? It's not easy to take a bottom-up approach, certainly in an area that has scientific and technological uncertainty, which is huge. And also you cannot steer academic research too much. It's like herding a herd of cats. right? That's a joke that always being said about academics. Secondly, in quantum computing, how should we join the race? What are the goals that we need to have? How do we advance toward the goals, and how much do we rely on the world? Should we have international collaborations in our quantum computer project, or should we be totally independent, and so on? So these are things that we're thinking about. We talked about international cooperation and also the issue of export and import limitation. So we're suffering already today from export limitations trying to buy technology. We expect this to become worse and worse, but also we're asking ourselves, if we have capability, should we limit the Israeli industry in what it can sell outside? And this is an interesting thing, how to regulate that, when to initiate this kind of regulation in order not to, strangle the Israeli industry on the one hand, but maintain an advantage in our friendly neighborhood around us. And that is actually the essence of how we keep national security here, because we cannot win by the numbers. We can only win by the brain power and the technological advantage. So with this, I thank you for your time, and I'll be happy to continue the discussion. Thanks.
Thank you very much, Tal. This was fascinating. I know I have so many questions for you and Chris, even though I come from Haifa, where we're the only institution that doesn't have the center
How
that
did you
you're talking
guess?
about. We still think about it. This is why you are here, right? We still realize the importance of the policy and legal questions. But I will keep my mouth shut because we have Shai Giron, who will also respond now, and then we will open up for comments, questions, discussion. Please, Shai.
I prepared something, but I need permission to share the presentation. I think I have one, and can you tell me if you see
Yes.
this the slides? Okay. So my angle is post-quantum cryptography, and my goal here is to just explain some of the advances that we have in this world. So I took some slides from colleagues at the NIST, the National Institute of Standards and Technology, from the team that is actually running the post-quantum crypto competition. Of course, they insist that this is not a competition, but in the world of cryptography, what people love the most is to compete against each other, and if you can break somebody's algorithm, this is the best delight. So it is a competition in a sense. And I took here a haiku from actually Daniel Apon, that you can read, and you will see my response in the end of this set of slides, and this is me here. You can see. So I'd like to just talk about classical versus quantum computers, but from the viewpoint of crypto, because quantum computers are here to solve big problems, to do good for the humanity, not to just break crypto algorithms. So this is just a byproduct. So crypto in general, or basically I would say public key cryptography, relies on difficult problems. There are some things that you cannot do on classical computers. So for example, the most famous example is RSA. The security of RSA relies on factorization. You cannot factor a very large number that is a product of two primes. You need some restrictions on how the primes were constructed, but that's basically the security of RSA. The Diffie-Hellman key exchange relies on discrete log, and discrete log on different groups, including elliptic curves. And now quantum computers take advantage of quantum mechanics and quantum bits and superposition, and they have a position that potentially they can increase some computations that are beyond classical computers. So what does it tell us? So is the sky falling? So if there is a large scale quantum computer that could be built, then we have some threats on public key cryptography. So RSA, ECDSA, this is elliptic curve cryptography for signatures, DSA, and Diffie-Hellman key exchange, all of the actually basic primitives that are used today for public key cryptography. And we also have problems with symmetric key cryptography, for example, AES and triple DES, and we have some problems with hash functions. So the big question is if in the large scale quantum computer, and if it could be built. So in order to really threaten these algorithms that I mentioned, you need a large scale quantum computer, and we are very far away from building something like this. So here are the things that are gone, RSA or Diffie-Hellman and so forth. And this means that NIST standards, the standards for digital signature, for key exchange and other primitives, they are gone, in theory, of course. Now for symmetric crypto, well, there are some good news. You just need to use larger keys. So AES, for example, comes with different flavors of AES with 128-bit keys. You also have a 256-bit key. And if you're using this, then you are good to go. I mean, there is no cryptanalysis known today that could be leveraged on AES except for the Grover algorithm, which is some kind of, let's say, a search in an unsorted list. But if you are using a 256-bit algorithm, then key, then you're good to go. So longer keys that are already existing and they are standardized solve this problem of the quantum computer threat. So we are good here. And on hash functions, there are hash functions today that we know that there is no algorithm, no quantum algorithm that threatens them if the digest is large enough, and okay, the compression function is using a large enough state. But we are good on this. The currently used algorithms are good enough here. I just want to say what we mean by good enough. We don't have any idea of a quantum algorithm that could be played on a large-scale quantum computer except for brute forcing that can compromise these algorithms. Whereas for public key cryptography, we do have algorithms. Now the question is if you have a quantum computer that is sufficiently strong. So this is the problem. Should we lose sleep over this? So how soon do we need to start worrying? So there are some people who are saying things. I mean, it's only a guess. So potentially it'll be something like 15 years to break RSA 2048 with a chance of 50% that this has happened. This is just like speculation. So we do have enough time to get prepared. But here is the but. In order to switch key cryptography to new style quantum safe algorithms, it needs time. So first of all, you need to build the technology, or actually to define the algorithm and to gain enough confidence. And this means a lot of analysis. And this is a very sensitive and time-consuming and effort-consuming effort to do the cryptanalysis. And then you need to think about the implementations and then interoperability. How are you going to play the game where some of the systems are using classical algorithms and some of them are post-quantum crypto algorithms, and of course you need standardization. So this takes a lot of time, and this is why the transition needs to start quite soon. Actually, the happy news are that it has already begun, in order to be ready with quantum safe cryptography if and when the sky is falling. So I will just describe what NIST has been doing. So in 2016, NIST declared this competition, and some requirements and evaluation criteria. They invited people from the cryptographic community to actually propose algorithms and convince the community and convince NIST that they are immune to the power of quantum computers. In 2017, after the announcement, there were 69 submissions for the first round. 5 of them were withdrawn because they were immediately broken. In 2018, there was the first workshop where people exchanged all the ideas and presented. And then in January 2019, there were candidates announced for round 2. So from 69 submissions, NIST reduces the list to 17 key exchanges, key exchange mechanism, and 9 signature algorithms. There was in August, there was the second standardization workshop, and round 3 was just recently announced in July. And there were 4 KM. KM is a key exchange mechanism. 4 key exchanges and 3 signatures, plus they also declared 8 alternates that are also in the final round 3 short list, but they will be perhaps standardized in the second phase. So first the real 3 finalists, and in January 2021, this is us. And the expectation is that between 2022 and 2024, we will have a draft of a standard. And the standard is probably going to include several options for key exchanges and for signatures. And then there will be some period for public comment, and it'll take time until there is a clear standard. And only then, the industry would be able to start actual deployment. So what about these possible replacements? Why don't we just do this tomorrow morning? So how do we do this? We just need to find a difficult problem that is hopefully resisting quantum computers. So we know that factorization can be broken with a quantum computer, but there are other difficult problems where there is a strong belief that they are not going to be solved even with a strong quantum computer, and they are based on lattices, on coding, on multivariate polynomials, and there are other tricks, and everyone has some pros and cons. I mean, there is no majorization, so there isn't one algorithm that is, or one method that is best on all aspects than others. Otherwise, the problem would have been very easy. So what we already know about this, and there was a lot of concern before 2016 about whether or not algorithms could actually be deployed, that the performance, which is a major issue of key exchange, signing, and verification, the performance of what we know will be probably the algorithms to be used, the performance is acceptable. Acceptable still means that the bandwidth and the computation time is much, much larger than what we have today, but it still is not breaking anything, and this is the good news. Of course, the cost would increase. And cost means that the industry and governments are going to pay a lot for increased bandwidth and more computations. Some of the ideas that were proposed are not plausible. They are not really something that you can deploy. For example, there were some good secure signature algorithms, but the key is so large that you cannot use it for a key exchange, for example. So some are not plausible, and it's not easy to have a drop-in replacement. So here is a nice picture that describes the second round. I mean, the first round had 69 algorithms. you can imagine that it's not easy to place 69 algorithms in a slide, but in the second round there were less. So this is more or less the list for encryption and key exchanges and for signatures. And you can see that there are different algorithms and they depend on different problems. For example, Crystal Kyber depends on lattices. And there are many that actually depend on lattices. There are some code-based algorithms like BI, classical Macaleese, HQC, LedaCrypt, and these were all discussed during and analyzed during the second round of this competition, and voila, in the end, some of them were eliminated because there was some dent or some problem, and NIST didn't want to take any chance. And here is what we have today. Finalists are the green, and alternates are in orange. Alternate means that this could be standardized, but after there is the first pick from the green ones, and this is the summary. So in the finalists, and I always look at the KEMs because in my view, this is the more urgent problem to solve. I'll explain why. Key exchange, we are talking about secure communication. So if somebody records today some traffic, some communication that where the key was exchanged with let's say Diffie-Hellman, and in 15 years somebody with a quantum computer can break this and decrypt this, we have a problem. So this is the more urgent problem compared to just signatures where there is time to solve this problem. So we have finalists here, some alternates for KMs and the same for signatures. And here is the end. So if we had this panicking haiku, I just wrote another one. We are prepared, we're not alone, good, problem is gone. Maybe, I don't know. And that's it.
Thank you for the optimistic haiku at the end. We need some optimism. If we could.
Well, I wanted to counter NIST's haiku that is a little bit optimistic.
Perfect. Okay, so we have several people on queue. We have Michal Gal and we have Ordo Kerman. I just want to very quickly introduce two things. I will not abuse my power too much as chairing this, and then open it up for conversation. I do want to say something more philosophical here, and then I want to say something a bit more legal, which deals with some aspects that were not discussed, and something philosophical about the relationship between law and the quantum state. Now, as most of the people around in this forum know, law is being challenged by the rise of very sophisticated algorithms and computing power, and the challenges are directed at several fronts. One such front is that, can law be replaced by sophisticated codes? And quantum, to the extent it's one of the algorithms that quantum can make a difference about, and that's debatable, or at least some aspects of law may be algorithmized in a way that so then will we have the same legal system in the next 20 or 30 years? And that is not just a matter of, do we have better materials, because it deals with something that is central to the way we live in a different manner. So it's not just, we have a better technology. This deals with our governance. This deals with something that we have to think about. So this is an ethical jurisprudential question that I'm putting on the table. The second observation relates to that, and that is something to do with it's a more ontological observation. Not the first is an instrumental question. Do we have to think about law being quantumized in a way that harnesses quantum computing? And how should we prepare for this? Should we prepare for this? Should we not? Because we understand that the drive is to military and money, but there's also law there. The second point I want to make is more philosophical, in the sense that we often debate in law, what is the relationship between the rule and the exception? Or the rule and the standard, on the other hand, right? So we have a rule in the particular case, we have a rule and a standard, which is a more loose, fuzzy logic type of phrasing of certain moral concerns that then should implicate the particular case. Now, what's unique about the quantum way of thinking is that precisely what Tal was telling us before, and that is that you have some features of the state of being, of the state of things, that are actually pretty relevant to the way we understand law. And that is the relationship of something which can be both this and that until being decided, that until you exit the quantum state. And then it's one way or the other. It has been binary decided, but it's only for this particular case. We think that then there was a precedent, but maybe there was. All our thinking about precedents and non-precedents and what is a rule and what is the application of the rule, maybe we should revisit our entire understanding of what law is once we realize that the quantum state, the quantum state of affairs is also relevant to the way we think about law. So these two things are more, let's say, more high abstract observations about the relationship between quantum and law. And I bring this only because, there's some also lawyers and lawyers with philosophical bent in the audience, and I want to engage them as well. The second observation builds up on the first one, and that has, and also builds on what both Tal, Shai, and Chris were saying, but it takes it to a different point. And that is, assuming that Chris is right and massint becomes more available, and assuming that Tal is right in the sense that sensing becomes easily available, and assuming that Shai is right that there's going to be attempts to decipher current cryptos, and even if Shai is right, there will be some lag time because not all systems will be able to transform in time, etc. Then challenges to democracy cannot be overlooked. Because to the extent that governments, I'm not just using China here because that's the easy culprit and, okay, we fear China, but even non-authoritarian states may have the capacity to build on existing regulatory designs and existing agencies as they are now, and top it off with quantum capabilities. And then, the idea of social control becomes something we should think about. So as we deal with import, export, who are our friends and who are our enemies, then how do we guard ourselves from ourselves becomes a major question. And that is not, it's not just, to answer that, we must revisit laws about quantum, but we also must revisit design question. How do we design some quantum technologies, having in mind the ability of quantum to capture us, being captured by authoritarian trends or social control-minded trends, so that we have a quantum ability to detect when quantum is being used in a manner that undermines democracy, if we care about this, to the extent we really care about this. Because I agree with both Chris and Tal in the sense that the sky could be falling, not tomorrow, but maybe in the near enough future, and we have to be prepared for that. So this is just my addition to the conversation. So I'm sorry I abused it's a response more than anything else. And I give the floor to Michal and then to O. Dunkelman. Michal, please.
This was fascinating. Thank you so much, three of you. I've learned so much, really wonderful. And my questions are mostly to Chris with regard to your policy, the policy part of your research. So the first one is really, what do you think is the most realistic scenario of those that you put forward, do you really think that there's going to be a Cold War, or do you think that it's a East-West issue? But I think a more fundamental one here is how different, when we think about our policies and our regulations and the rule of law plays, how different is quantum technology from other types of technologies? Do we need to reinvent the wheel, or can we learn from other technologies that we've regulated? I can think about, the atom, for example, and other types of technologies that can actually serve as, case studies, and we can learn from them to quantum. So where do you see, or how do you see that quantum is different with regard to regulation and with regard to the rule of law applied to it? Thanks.
Okay, or please.
So I just want to comment a bit on what was said both by Tal and a bit by Shai. You have to remember that cryptography actually is composed of several types of things. We also encrypt data, but we also exchange keys for encrypting the data. And that means, for example, that if, as Shai mentioned, you break the key exchange, you can afterwards decipher the data. But there is another primitive, as Shai showed on his slide, which is signatures. And digital signatures are very important from a perspective of law, actually, because today we authenticate data digitally and we sign it digitally. And a document which was signed today is going to be disputed in 100 years from now. So actually, if there is an urgency in shifting towards post-quantum security, that would be first signatures, then key exchanges, and then needed encryption. One thing to remember about the encryption, the quantum key distribution, that at the end, unless you have the more advanced stuff, but the basic ones, for example, the one that the Chinese are using, already assume that Alice and Bob, the two famous players, already exchanged the key and they know each other. So the basic quantum key distribution, the one which is deployed at the moment, assumes that Alice and Bob has already met. And there is one problem here. I don't know how many of you met Amazon. I mean, I once met Alibaba Express. I just went outside and spoke with him. But the thing is, this is not a solution for the layperson and us. This is for, banks speaking with banks, governments with governments. This is not going to be the basis for the new internet. What we need is indeed the post-quantum cryptography, which allows us to do that and still maintain security under the assumption that some mathematical programs are untraceable on quantum computers. And we hope that we know what to do. Emphasis on hope, but don't worry, we also hope that we know what we're doing at the moment. So the fact that this conversation is encrypted using the same primitives that we hope that we understand they are secure at the moment. So don't worry, we got it under control, I think.
Okay, I want to join on this. Just another question for Tal, and to sharpen the debate between Tal and Chris, and then we'll open it for a round of comments on each other by the panelists, and then we'll open for just one more round of questions from the audience. Now, Chris mentioned something that I think with which Tal disagreed, and that is the risk for winner takes it all, in which Tal was saying, look, the ecosystem as it is developing between Amazon and IBM, Microsoft, is such that it builds upon the notion of the cloud and builds upon the DNA of the academic community and the industry to share and find ways to make money. And that has a built-in logic to it that defies or resists closing off or walling off some aspects. But Chris was saying that perhaps with respect to materials, some things will be blacked in a way so that the jump will be such, to use Tal's analogy, that then if you don't join the club, or if you're preventing from joining the club, the leap will be so far that there will be a club that you will never be able to join. And that also relates to what Michal was saying, like the club of people who have an A bomb, of countries who have an atomic bomb or something, is going to be it's going to be so difficult to join, in which case then you have other type of governance problems, because, the question becomes one of, if only very few governments, or even two governments only, have such capabilities that nobody else can reach because they keep using the technology to leap ahead, it's never going to be static, right? So with atomic technology, it's somewhat static. I mean, you developed it and then, okay. But if quantum can keep advancing, using quantum to advance the quantum, et cetera, then we have an issue. And I would like some comments on that, if you think it's worth our time. So please, let's do it in the order that you addressed us. So Chris, Tal, and then Shai, the floor is yours.
First, thank you to Tal and Shai for sharing the stage with me. Your presentations are excellent. I've taken pages of notes, clarifying, are really wonderful. And there's also a great series of questions here to think through. Obviously, I can't get to all of them. So let me start on the philosophical issue. We spend a fair amount of time talking about James Scott's famous book. The title of it has escaped me. It discusses the phenomenon he calls authoritarian high modernism. And this is the idea that you have these kind of technical gods who say, I'm going to fix society and I'm going to do it with technology and we're going to perfect systems. And Scott talks about things like engineered tomatoes and so on, the different technologies through the last century that were engineered but turned out to be kind of bad. When you today, not even going into quantum, just today, if you pick up and you read Google's vision for sidewalks, you realize that, related to your concern, like the philosophical question of what law is, if you lived in Google's sidewalks land, you would have to live in a very different way. You could never jaywalk, for instance, because the computer is controlling the direction of the traffic, and traffic can change directions and change lanes for optimization purposes. So we have to move away when we start thinking about these plans of, let's say, citywide traffic routing. We as individuals have to give up our selfish routing to the oracle, and I don't think we even have to get to quantum to realize that there are already people who are proposing these types of systems today, and they create profound problems for governance and for the individual. And like, what are lives? Will I be free to walk the wrong way down the sidewalk in the future? There's so many good questions here, and I could go on about them. On the issue of scenarios, I actually think the public-private scenario is most likely, and the reason why is there's some very specific things about building quantum computers that put people at, let's say, the UC Berkeley's in the world at a disadvantage. And that is that our service and teaching requirements literally get in the way of building a big device. And we've interviewed a lot of people for this book. And researchers at universities have told us that they have made smaller devices because of compromises in their obligations. Whereas if you're at a Google and you have billions of dollars in cash, and you have support from Eric Schmidt, and you don't have any publication requirements, no teaching requirements, no service, and you're living in Santa Cruz, that's a way to get ahead. The same is true in the labs. The labs are free of some obligations. And then, and I think Tal's presentation really elucidated this. There's this whole kind of shadow market that no one talks about, and that's the Northrop Grumman's, the Raytheon BBNs, basically the defense companies that are building these things without any publicity, without any kind of public dialogue, without any public reporting, and so on. And I think they very well could run away with the prize, but given the resource constraints that universities have. I really want to hear from the other panelists on some of these questions, so I'm going to yield back my time.
So the floor is yours, and just like Shai told us that the sky do tell us that there is oversight over what's going on in some of the black side of, with respect to democracy, with respect to how is it's going to be used.
Okay, I'll try. First of all, the discussion is really interesting. Not my usual discussion.
This is what happens when you come to Haifa, you see.
Yeah. So first of all, to your comment, Amnon, I think that if we will find a quantum algorithm that will reduce the number of lawyers, that will be a huge motivation for quantum computing. So yeah, just give it to me and I'll push it.
I agree for the reasons Chris said, because there will be more time for me to do research and less time to teach. So that's great. I'm with you.
I think that it's early to say how fast quantum computing will evolve. And certainly we are all looking at Shor's algorithm, which was defined in the mid-90s for factorization. And we say, okay, let's look at these post-quantum families of algorithms that we do not know, and we have some assumptions that they will be immune to algorithms like Shor. And as Shai mentioned, in about 10 or 15 years, we'll be able to push them to the market. But you have to understand that the market in quantum computing is not staying at the same place. It's moving ahead. People are looking at algorithms all the time, like the one that I mentioned today, that was discovered about partial differential equations. So this will be an armament race, if you would say, or like the virus and antivirus. So I say that we should not go into panic, but we certainly need to be very well aware of what the capabilities are and how fast they are going. Because as Shai said, changing the encryption methods is not an easy thing. The NIST process started in 2016, and it will be maybe ready for implementation in 2024, and the market is moving very, very fast. So I don't have any further insight, or I cannot make promises about that. I can tell you that as much as all of the smart people in the crypto community are thinking about these post-quantum cryptography algorithms, there are other smart people looking at the other side of the equation. Secondly, it's very important for me to stress that quantum computing will have an impact not only in stuff that has to do with privacy and cryptography and stuff. That will be far away. Much before that, there will be optimization problems. So for example, there are calculations about materials that involve nitrogen compounds that are very relevant to either explosives or to fertilizers. And the simulations about this field take up about 2% of the global energy consumption every year. This is huge. You can think about if there will be a country that will manage to find and build a quantum computer that will do this optimization problem. The impact will be huge, both in the defense side and also in the economic side. And if you take that a little bit further in your thinking process, you can change the nitrogen compounds with carbon compounds and understand what will be the potential impact on climate change. Okay, so the sky is really the limit. I don't know if the sky is falling, but it's a big sky. For what Michal mentioned about atom bombs or nuclear weapons, I think that a very significant difference between the two things is that building an atomic bomb is not an easy thing to do and has not been easy ever. Building computers is something that starts up very cumbersome and difficult, but it becomes easier and easier. So I stole this picture from Yuda Naveh from IBM Research Labs in Haifa. Actually, he just left there to found one of the Israeli startups in quantum computing. And he shows on the left-hand side the first classical computers by IBM from the 1940s and the IBM quantum computer from about a decade ago, and they look kind of the same. And this is like a visionary image in my mind, because we know the left-hand side where it got to, and that we all have computers in the palm of our hand all of the time today. So we can think about what will happen to quantum technology. Okay, and this does not happen in atomic bombs. You don't see small atomic bombs being distributed to massive quantities of people, but you do see that in quantum computers, because the technology in its essence is not that difficult. It's not that complicated. The fabrication methods for superconducting qubits, like IBM and Google are making, are not very much different than the fabrication processes in the Intel chips that you have in your phone or computer. And I think this is a fundamental difference between them. Yeah. Thanks.
Shai, do you want to comment?
I'm hiding behind.
You're hiding behind.
Yes, yes. Sorry. Here I am. Back. I just wanted to say that I spent something like 15 minutes on talking about cryptography and the threat of quantum computers to cryptography, but the hope is actually that quantum computers would solve significant problems for humanity. And this is just a byproduct that we in the crypto community are happy to play with.
So just a question, Shai,
Yeah.
wouldn't supercomputers also be able to develop keys that are so much more secure that then quantum computers will have difficulty in so I'm just saying whether there's also a market for cryptography, not just for decrypting things, but that's, I guess.
Okay, I can give an example. For today, if you're looking at RSA, the standard is to use public keys with size of 2,000 bits, let's say 2,048 bits. You can, in theory, of course, increase it. So there is some prediction with Shor's algorithm that you can factorize numbers, and let's say that you have a quantum computer with so many qubits and so much power, and you can just, okay, say, let's do 10,000, 100,000 bits RSA, but this doesn't solve the problem fundamentally, because if you have, then quantum computers could also grow. So this is not considered today as the right approach. We are trying to look for problems where there is some indication and belief and maybe some analysis to convince us that quantum computers will not be able to solve, not just by brute forcing, In symmetric cryptography, this actually works. So AES, if you just use it with two 56-bit keys, then you're good to go, because all that you can do is what's called the Grover algorithm, and it's like brute forcing a key.
You can use quantum key distribution, which is fundamentally different because it relies on the physics.
Yes. Quantum key distribution is a quantum technology. I'm talking about post-quantum cryptography, which means to design today an algorithm that could be used with classical computers and would resist.
Not today. But if you think today about ways to harness quantum, so once you have quantum, you can say, okay, we're in the clear, because quantum then also allows us to.
Yeah. Okay. Well, I'm thinking these days with some partners actually on doing quantum signatures, for example, but with a quantum computer. I don't have a quantum computer, but.
We'll buy you one. Doesn't
it's okay. It's okay to think, all right. But this is a completely different direction in cryptography, completely different from what I was talking about.
If I could chime in on this, what we talk about in the book is how institutions have to think about the secrecy value of their information. For a lot of businesses, their information is only really valuable. The secrecy is only really valuable for a series of just a few years. Like, your business plan is not useful 15 years from when it was developed. So you have to think about the value of your secrets. For governments, the United States has liberalized its classification. Most documents in the United States become unclassified after 25 years. So that might be a way of thinking about how much forward secrecy you need. But I agree with Or that the attacks are not going to be on individual messages. the estimate is best case scenario, it would take 8 hours to factor a single key. Now, if you have a tasking order and you have this device, you obviously are going to focus that attack on signatures, and you're going to use it to poison software updates. And I think that's the tip of the tip of the spear is to think about software updates and corrupting those, because once you've broken into this device, you get all of my messages. Anyway, key value is very important. It's also important to note that, even the Google people say, if you were able to build this machine, it would take a full 8 hours to do a single key. And so that's an important resource constraint to think about. And then thinking back to the cloud model, one of the interesting things about the cloud model is, let's say I'm Amazon and I'm hosting, Rigetti and so on. In principle, you could look for people using the devices to factor and just not let them do it. Just as a policy matter, you're not allowed to use my cloud-based quantum computer to factor keys. You're going to have to use it for something else. And that's like one upside, I think, of the cloud model to consider.
So that's back to the importance of integrating the development with thinking about regulation, which, if there's anything that I think I take out of this, is that how important it is. And, Tal said it jokingly, let's, use the computing, the quantum algorithm to channel lawyers away from lawyering, let's put it mildly. But I take it on the reverse. I think that we will need greater legal attention to what's going on here, because once we wake up and we realize, yes, Tal, once we wake up and we realize all the things you guys can do to affect the way we live, we're going to say, wait, this can be used to corrupt this and can be used to corrupt this and channel that and engineer this. And wait a minute, we got to think about that, because currently some decisions are being made by people who have other incentives in mind, which are important incentives, but nonetheless might not include all considerations that we care about. Just think about the amount of time we currently invest in using technology for fairness, or to ensure that technology is used in order not to discriminate and in order to provide access to this, that, and the other. And we do this now because we all of a sudden realize that, it's happening. It has been happening by the industry, and now we're trying to catch up, to play catch up. Now, once we move to quantum computing, I think, and if we don't learn from our mistakes in the first wave of AI, then we might face challenges once quantum computing is embedded in making certain choices about who gets a loan, who gets to get what type of position in all kinds of, who gets to get what type of medicine, etc., etc. All those distributive decisions, if they're done by an algorithm that runs on quantum computing, then I think, and we haven't thought about it before, by the time we start to thinking about it, might be a bit too late. Any ending comments by the panelists? Because unless we have some questions or comments from the crowd.
Just wanted to say thank you.
Yeah, that's exactly what I wanted to say. Thank you. It was a very rich conversation. Thank you.
Hopefully, we will be able to have a revisit of this panel or something like that, because we are thinking of maybe instituting a yearly conference on quantum and the law, just to see what type of developments have been done and what type of regulatory challenges do they raise, in order not to wake up one day and say, oh, look what just happened. The sky has started to descend on us. With that on mind, Happy New Year to everybody. And hopefully we'll harness the quantum to solve. The next time we meet, there will be no coronavirus that actually endangers us. And with that, I end our, it's 8 o'clock now here, and I end the panel. Thank you again, panelists. Thank you, the participants, for sharing your thoughts. It has been really, for me, it was very stimulating. Good night.
Bye.
Bye.